Okay, so the first chapter is on units and measurements. Um, this is one of the easiest chapters. It just gives you an overview of physics. Okay, I mean sort of an intro to physics. Right. What do the laws of physics apply to? Everything. Okay. No matter what happens in nature, they have to obey the laws of physics. Okay? Now, here's the very neat thing about it. In nature, there are so many complex things happening, so many different phenomena happening. Okay? And all of those are covered by just a handful of the laws of physics, are very few. Okay? Do you know how many laws of physics there are? I'm sorry? Well, 4 actually. So there are only 4 forces: strong force, weak force, at least at these energy levels: weak force, gravity, and electromagnetism. Okay. So all those phenomena are governed by very few laws. Okay. Now it turns out that a lot of the laws that we study are approximate laws. Okay. So for instance, gravity, the real theory of gravity is quantum gravity. Okay. But that's too complex a theory. Newton's law, which is an approximate theory, is good enough to describe the planetary motions and stuff like that. Okay? So the weak gravitational fields that we'll deal with, and not very massive objects that we'll deal with, Newton's law of gravity is good enough. Okay? All right. So anyway, physics governs everything. Okay? No phenomenon in nature occur that disobey the laws of physics. Okay? All right, so here is just a little example, just to give you the different scales on which the laws apply. Okay? So here, these are atoms. Okay? The size of an atom is roughly 10 to the minus 10 meters. Okay? Here are microorganisms that are about 10,000 times bigger than these atoms. Okay? So these are about 10 to the minus 6 meters, roughly. This is 10 to the minus 10 meters, 10 to the minus 6 meters. And these are colliding galaxies. Okay. And they're 300 million light years across. Okay, the 100 million, 10 to the 5, about 10 to the 21. Yeah. So this object is about 10 to the 21 meters across. Okay. So you see about 30 orders of magnitude difference. And the laws of physics apply to everything. Okay. From microorganisms to macroscopic objects. All right. So this picture is taken using a scanning tunneling microscope. Do you guys know what that is? All right. So, like it says, okay. So let's say this is this metal, that's that surface, and you want to take a picture of that. Okay? That's what this is. Okay? So here's what you do. You take an electrode. Okay? So let's. So here's the surface on which of which you're taking a picture. Here's an electrode with a sharp point, and what you do is you apply let's say 25,000 volts or something like that between the two. And then what you do is you keep this electrode level and scan the surface. Okay, so you're scanning the surface. Here's what happens. Okay, every time there's a bump on the surface, electrons are tunneling between the two. Electrons are tunneling. Smaller the gap, what happens? I'm sorry?
Does the charge go down?
Okay, what is the difference between this? What is the difference between here and here? I'm sorry? I'm sorry?
It's denser.
Yeah, there are more electrons. The smaller the gap, more electrons will tunnel. Okay, the current is higher. So as you're scanning the surface, all you're doing is measuring the current. And this is just a translation of the current. Okay? So this is proxy for the current intensity. And that's a scanning tunneling microscope. Okay? So you're just measuring bumps. Okay? All right, so that's where the name comes from, scanning. You're scanning the surface. Tunneling, you're measuring the tunneling current, and you're using this to look at microscopic objects. So that's where the name comes from. Right? Anyway, so that is that. All right. Now, how do we discover laws of nature? We make observations, or we go sit down in a room and think about things, and either you discover laws experimentally, or you come up with theories. Okay? And if you come up with theories before anybody starts believing in you, they'd have to do experiments to verify your theories and your predictions. Okay? So we have to do experiments in science. And it turns out that every quantity, so this is absolutely amazing, every quantity that you measure in science can be expressed in terms of 7 basic quantities. Anything you can think of that you measure in science. So for instance, here's various things that are measured in science. And every one of them can be expressed in terms of these basic quantities. And these are length. So here's a unit of length, meter. This is a unit of mass, kilogram. This is a unit of time. Yeah. This is a unit of current. Yeah. So flow of charge, electrical charge. Yeah. This is a unit for temperature. Yeah. This is a unit for amount of stuff, the number of molecules, for instance. Yeah. And this is a unit for light intensity. Yeah. So it turns out that anything that you measure in science can be expressed in terms of these 7 bricks. Okay. And these were the units adopted by an international body. Okay. And we'll talk about them. In this semester, every quantity we study can be expressed in terms of these 3 quantities. Okay. So every house that we build will be using only these 3 bricks. Okay, so for instance, velocity is meters per second. Acceleration is meters per second squared. Okay. Force is mass times acceleration, kilograms times meters per second squared. Okay. All right. So everything that we study will be in terms of these 3 guys. All right. Now smaller. So let's do a meter. What is a meter? A meter is here's a meter. Okay. So this is a meter. Now here's the problem. So we have a lot of biologists and stuff like that. What do biologists do? They study cells. This is not a good unit to measure cells. Okay. So what do? This is the basic unit of length. So here's what we do. So scientists are pretty smart. What they do is we derive a unit. Here's the meter. That's the basic unit of length. And if you put a prefix, what the prefix stands for is a power of 10. Okay, so this micro, the prefix micro stands for 10 to the minus 6 meters. Okay? Now this is a good unit to measure the size of a cell. Okay? So all you have to do is you start off with a basic unit and attach a prefix to get an appropriate unit for whatever it is that you're studying. So for instance, if you're a nuclear physicist, okay, so here's an atom. So here's the hydrogen atom. Well, let's do a different one. Let's do a helium atom. Okay, so here's the helium atom. There's the nucleus with 2 protons, 2 neutrons, and 2 electrons. What is the size of an atom? I'm sorry? Very good, my friend. See, somebody's listening and paying attention. 10 to the minus 10 meters. All right. This nucleus, anybody know the size of the nucleus? It's 10 to the minus 15 meters. The nucleus is 100,000 times smaller than the atom. So to give you a picture that's more memorable, if the atom were the size of a football stadium, the nucleus would be the size of a marble. The nucleus is tiny. Yeah? And that's where all the mass resides. In chemistry, all you're doing is messing with these outermost electrons. You're never touching them. So in bigger atoms, you're not even touching the inner electrons. All you're doing is touching the outermost electrons. All right. Anyway, so if you were a nuclear physicist, your unit would be that. And that is a femtometer. Yeah. Femto in honor of Mr. Fermi, okay, who was a nuclear physicist. So if you get a unit named after you, that means you made it. All right. Yeah. You have a question? Right. It is roughly that. And all right, let's talk about why. Okay. So I'm just making, all right, what the heck? All right, here's a carbon atom. It has 6 protons. What do positive charges do to each other? They repel each other. Why aren't these guys flying out? I'm sorry?
The negative charge, of course, and then push in.
No, that's a very unstable configuration. So
Is it the neutron? They're gonna...
neutron is neutral. All right. So why aren't those protons flying away? So like I said, there are 4 forces: a strong force, an electromagnetic force, a weak force, and the gravitational force. Okay, so the electromagnetic force is what's making them repel each other. Yeah. So if they're not flying apart, there must be a stronger force holding them together. And it is the strong force. And the strong force is 100 times stronger than the electromagnetic force. Okay, so if there's an electromagnetic force that is repelling them, a stronger force, the strong force, which is 100 times stronger, that's holding them together. Except that the strong force has a range of 10 to the minus 15 meters. So you have to be that close before the strong force can come into play. That's why all nuclei are roughly that size. Okay. All right. This guy is a million times weaker than the strong force, and this guy, we don't even talk about him. Again, that guy is so weak that we don't talk about it. No, we will talk about him. So the point is, if you're talking about this guy, none of these guys are in play. Okay. So when this guy is in play, you can ignore all these guys. When this guy is not in play and this guy is in play, you can ignore these guys, and so on. Okay. All right. All right, so we saw that all these quantities that are measured in science can be expressed in terms of the these seven quantities. So for instance, we'll talk about energy. Energy is measured, the SI unit for energy is joule. And again, all these units are named after scientists who made major contributions in these fields. Joule, that's the symbol. It's Newton meter. Here's joule expressed in terms of another composite unit. And here's joule expressed in terms of the basic units. Meter square, kilogram per second square. Force and so on. Okay. And so you saw the use of prefixes. Okay. Again, if you wanted to measure the distance to Jacksonville, for instance, this is not a good unit. Why is this not a good unit? I'm sorry? Yeah, that's right. The distance to Jacksonville is 150,648 meters. And you'll never remember that. Okay. Why won't you remember that? What's that? Yeah, I mean, you're too smart. You don't want to waste CPU on remembering that. So you're hardwired to remember small numbers. Okay? So 150 kilometers. So this prefix is 10 to the power of 3 meters. Okay? So that's the distance to Jacksonville. Okay? All right, so using prefixes, you can derive various units. Units that are appropriate to the field that you're working in. Okay. All right, the unit for time is the second. And nowadays, scientists do very accurate experiments where they can measure things very precisely. So you have to define your quantities very precisely. So for instance, do you guys know the distance between the sun and the earth? Roughly 100 million miles. And again, the size of an atom, very tiny. Have you ever seen an atom? Well, no. Will you ever see an atom? You've seen evidence of an atom. Okay. You guys have heard of gravitational waves? Okay. So they detected the first gravitational wave in 2015. Okay. And we'll talk about it later. Okay, so here's what happens, roughly. Okay. So this is the sun and this is the earth. And let's say some event happened here and a gravitational wave passes by. And when this gravitational wave passes by here, what happens is the distance between the earth sun increases and decreases. Okay? So they go, the distance increases and decreases like that. Okay, so that distance will oscillate. And they measured this the first time in 2015. They didn't measure this distance. The experiment was done in, the detector was in Louisiana, and there's one in Washington, the state of Washington. Yeah. This is absolutely mind-boggling. I'll tell you the fact, but you'll have to go think about it for several days, and it was still hard to comprehend. This 100 million miles, it changed by the width of an atom. And we measured that. Okay, so this gravitational wave passed, this distance changed by the width of an atom. Okay, so it's absolutely amazing. All right, so anyway, so we have to define our quantities very, very precisely. Okay, so here's the definition of time, the current definition of time of a second. Okay, so so here's the model of an atom. Here's an excited atom. So excited atom just means that, all right, no. Okay, so here's a carbon atom with 6 electrons, and it's got 6 protons. And what you could do is you could excite this carbon atom by getting one of the electrons up there. Okay, and if you excite this atom, it generally will stay there for about a billionth of a second, maybe a trillionth of a second, and this electron will fall back to its ground state. And what happens in the process? I'm sorry? Yep, it emits a photon in the process. The energy of this photon, again, is the Planck's constant times the frequency emitted. Okay? And this energy is exactly equal to the energy difference between these two levels. Okay, so that's how you can get the electron excited as well. If you send in a photon, this electron will get excited from there to there, and when it falls back, it emits this photon. Okay. Every atom has many, many different energy levels. Okay, so every atom can emit photons that are identifiers of the atom. Okay, so for instance, when the forensic people, when they identify stuff in a crime scene, all you have to do is burn some of the stuff, watch the light coming from there, and you know what compounds were in there. Yeah. So the light emitted for every atom, molecule, and all they're unique. Okay? So they're their fingerprints. All right, I'm telling you this to define the second. Okay, so this is the very precise definition of the second. All right, so we're going to take a cesium atom. So this is one transition, there's another transition. There's an infinite number of levels. We're going to take a cesium atom, we're going to take one particular transition. We're going to look at the light coming from there. And by the way, if you have a whole bunch of photons, They become like a wave. And this is the electric field. So let me show you an electromagnetic wave. Right, so here's an electromagnetic wave. Why is it called an electromagnetic wave? It's got electric fields and magnetic fields in it. Okay, and so here's a light beam traveling in this direction, and if you're standing there, what happens is if you're so okay, so here's a light beam, and if you stand here, oh, it died. If you stand here, you measure the electric field. The electric field is oscillating like that, and the magnetic field is oscillating like that. Okay, so what we're going to do is we have a cesium atom. It's emitting light. We're looking at one particular transition. We're going to measure the electric field oscillating. You guys following that? And so you're counting, here's the electric field, that is one oscillation. Okay, so the electric field going like that, going back and then back up, that's one oscillation. When 9,192,631,770 oscillations happen, 1 second is passed. So that's the definition of a second. Now there's a couple of things about this. So why do we need such accurate definitions? Do you guys know how the second was defined, how time was defined back in the day? I'm sorry? The position of the sun in the sky. All right, so back in the day, the sun was here, came back there, that was 24 hours. Okay. And it turns out that we do that today and you do that tomorrow, that 24 hours is not the same. Every day it's changing. If the Earth's orbit was a perfectly circular orbit, then it would have been the same. All right. And that depends, this definition of your time depends on you being on Earth. What happens if you have a buddy in the next galaxy? How do you explain the second to him? Right? What? No, he doesn't know it. Okay. It's hard to explain that time to him. But this definition using cesium clocks, cesium atoms, he's got cesium atoms. Okay. And he will know the definition in a second. So, these definitions are all universal. You can talk to your buddy in the next galaxy and he will understand your unit of your fundamental unit. All right, so that's the definition of the second. By the way, this is Planck time. We believe that's the smallest unit of time. Okay. Here's an atomic clock. Again, probably uses cesium. So again, to define this time, you had to have a cesium atom that was emitting this photon. Now, here's another thing that you have to make sure of in those atomic clocks. You guys have seen when you're driving, if a siren is coming toward you, what happens? The pitch is sounding higher. The perceived frequency is higher than the emitted frequency. And when the ambulance moves away, the pitch is lower, the perceived frequency, the detected frequency is lower. You have the same problem here. If the cesium atom is coming at you, the frequency you see is higher than the emitted frequency. Well, your definition was that precise, and if the cesium atom is moving, it's all messing it all up. What do? So you make it very cold so they're not moving as fast. Okay. So that's how you. Okay. Anyway, so all that kind of stuff you had to worry about. Okay. All right. Here was the definition of the length. This was back in the old days. Okay. Again, this definition is not universal, so 1/10 millionth. Okay, so this distance going through Paris was defined as 10 million meters. Okay, and that was the shortest distance, assuming an Earth flattening of 1 to 334. Okay, the Earth is not a perfect sphere, so you can go to the Wikipedia page there. But anyway, here's the definition. The Earth is not perfectly flat, it's an ellipsoid. Okay. And this 334 means A minus B divided by A. Okay, so A minus B is 1 for every 334 miles. So what this number is saying is, for every 334 miles that you're going here, the Earth, if this was 334 miles, this is 333 miles. That's how much the Earth is flattened. That's what this number is telling you. Okay. Anyway, that's just an aside. Okay, so the meter was this was 10 million meters. Okay. Again, that's a very Earth-centric definition. We want a universal definition, and here's the definition of meter. By the way, the speed of light is constant. Okay, and we believe it's the same constant everywhere. Okay. So you've already defined the second in terms of the cesium atom, which everybody in the universe understands. Okay. So the meter is the distance light travels in this amount of time. And here's something that everybody will understand. Okay, and it's a very precise definition. So mass back in the day was defined as the mass of this lump of stuff. Okay. That was a kilogram, this sitting in Paris and stuff like that. What's the problem with this? I'm sorry? I'm sorry? Why would it change? I'm sorry? Why would it degrade? So it could react with stuff. So that's why you have it in an inert atmosphere.
Like gravity changes, they can take to the moon and way less.
Yeah, no, mass is not a force. It's it's amount of matter. What happens if an earthquake happens and that thing gets destroyed? It's a sample, right? It might react, this, that, and the other. So now we have a definition of a mass. This many atoms of this element are in a cage. Okay? And again, that's a universal definition. But anyway, this was the old definition of a kilogram. And every kilogram that you go to the store has been eventually weighed against that. Okay. So they've taken this sample and weighed other samples against it, and those are floating around. Okay. Now we want to understand this expression order of magnitude. So, by the way, so we okay, so we saw numbers. The order of magnitude of this number is that, -2. The order of magnitude of this number is that. So the power of 10 that the number is closest to is the order of magnitude. Okay, so 856, that's close to 10 to the power of 3. So the order of magnitude of this number is that. Yeah, 15,460. What is the order of magnitude of this number? This is closest to 10,000. So the order of magnitude of this number is 4. Okay. So how about 125? The order of magnitude is 2. Okay. Oftentimes, for instance, we are just the reason we talk about this is oftentimes we are interested in an answer just to the order of magnitude. So in astrophysics, if you're doing astrophysics, nobody can ever give you a precise number. It's just ballpark numbers. Okay? We'll do a little calculation in a second, a Fermi calculation, and then you're more interested in order of magnitude. Okay, so order of magnitude is just that. Okay, so 800 is close to 10 to the power 3, and the order of magnitude is 3. Here's a precise way to calculate the order of magnitude of numbers, but we won't be interested. We won't do that too many times. So if you wanted to calculate it precisely, what you do is take the log of that number to base 10 and then round the log to the closest integer. Okay, so log 800 is 2.9, and that's close to 3. So that's how you get that. Okay. So here are some order of magnitudes. So the size of the visible universe is that. Okay. 1 light year is 10 to the minus 10 to the 15 meters, 10 to the 16 meters. What is a light year? What is a light year? The distance light travels in a year. Okay, why do we define this? I'm sorry? Yeah, well, I mean, it goes back to the fact that depending on what distances you're measuring, you use appropriate units. So if you, for instance, we live in a spiral galaxy, the Milky Way, and kilometers and miles are a bad unit to measure the size of this guy. The size of this guy is about 100,000 light years. Okay? So when you're measuring astronomical distances, this is a good unit. Okay. So when you start talking about the size of the universe and stuff like that, that's a good unit. So the size of the visible universe is about 42 billion light years. Okay, so the furthest object that you can see today is about 42 billion light years away. Okay, the cell is about micrometer, 1 to 10 micrometers. Here is the size of an atom, the size of a nucleus, okay, and so on. Here are some masses. Okay, the mass of an electron is about 10 to the minus 30 kgs. The mass of a proton is about 10 to the minus 27 kgs. A proton is about 2,000 times heavier than the electron. Okay. Here is the mass of, roughly the mass of the visible matter in the universe. Okay. So you guys might know that now this is the composition of the universe. So this is funny. 25% is roughly dark matter. 5% is normal matter that you and I are made of. And 70% roughly is dark energy. Okay, what is dark matter?
Doesn't it like pull things together, or is that dark energy?
Dark matter pulls things together. Dark energy makes things fly apart. We call it dark. Why do we call it dark? Huh?
It's not visible.
No, we are in the dark about its nature. We don't know what it is. Okay, so 95% of the universe, we don't even know what it is.
We'll get there.
What's that?
I said we'll get there.
Yeah, we'll get there. Yeah.
What's that last slice of the pie?
I'm sorry?
What was the last slice of the pie?
Normal matter. 5% is normal matter.
Oh, I thought there was a
That's my bad drawing capabilities. An artist, I'm not. All right. So here are some numbers again. Age of the new universe. The universe is about 13.78 billion years old. The Earth is about 4.55 billion years. Again, these are all times in seconds. Duration of a nuclear collision, 10 to the minus 22 seconds. That's not an easy thing to measure. Okay. You know, UCF has quantum optics groups. They can fire these lasers. Okay, so here's this laser beam. Let's say, did you see that? I turn it on and off, and I'll fire a small pellet of the laser, right? So UCF can fire 10 to the minus 18 seconds. Okay, so let's look at the length of that. CT. So UCF can fire laser beams like that. Well, UCF and many other places. And this thing, the length of this thing is 3 times 10 to the minus 10 meters. How big is that?
Not very big.
Huh? It's 3 atoms. There you go. Now, why the heck would you do that? What's the use of it? So imagine this. There's several chemical reaction going on. you want to study, you guys know about strobe lights? What do strobe lights do? If they're shining lights on and off, and as for a dynamic phenomenon, you can see it at a different stages. You could use this to study chemical reactions as they're in different stages. You know? That's just one of those things you can do. All right. Okay, I'm going to finish this quickly. So oftentimes we have to convert units. Okay, so for instance, here is a speed in miles per hour, and we want to convert it into standard SI units, meters per second. Okay, so here's what goes into conversion of units. 1 mile is 1600 meters. Okay. So what is 1600 meters divided by 1 mile? What is that? If this is equal to that, that divided by this is 1. This is 1. That's unity. Okay. What is 1 mile divided by 1600 meters? I'm sorry? They're all 1. Okay. All right, so when you're converting units, okay, what is 5 times 1? 5. So I can multiply a number by unity all day long. Okay, and that's what's happening. So here's 75 miles an hour. I'm multiplying this by unity. I'm multiplying this by unity. Okay, so in converting units, what you're doing is you're multiplying by appropriate factors of unity. Okay, how do I decide if I want this or this guy? Well, it depends on what it is that you want to cancel. Okay, so 75 miles an hour is 33 meters per second. Okay. So conversion of units is just saying the same thing in a different language. Okay. Okay, so here's this equation. This stands for distance, velocity, time, acceleration, time. Okay. Now you don't need to know any physics, but I'll tell you a technique to see if this equation is correct. Okay. And that's dimensional analysis. Okay, so here's an equation. Okay. And so here's the simple fact. If you have apples on the left-hand side of this equation, what do you need on the right-hand side? Oranges, pineapples, apples. You need apples. Okay. So if you have apples on this side, what you need is apples on that side. So if this is distance, if this is length, this had better be length, that had better be length. You can't have length here and length here, this term being length and that being area or volume. That doesn't make sense. Okay? And that's dimensional analysis. Okay? So this has dimensions of length. Yeah. Velocity is length over time, and then multiply by time, plus 1/2 is a number, it doesn't have any dimensions. Acceleration is length over time square, and then time square. Yeah. So you see, this equation has potential to be correct, because on both sides of this equation, What you have is apples on both sides. What can mess it up? This, by the way, is the correct equation, but what could mess it up? Well, the correct equation has 1/2 in it. It would be dimensionally correct for any number there. Okay, so this dimensional analysis can tell you if an equation has the potential of being right, but it can't tell you if it is the right equation, because this dimensional analysis verifies the correctness only up to a constant. Okay? This equation happens to be correct. But this technique is good because it can tell you this equation is not right. Okay? Because that equation doesn't have apples on both sides of the equation. Okay? So dimensional analysis can help you eliminate wrong equations, billions and billions of wrong equations. Okay? So Mr. Fermi was a brilliant physicist, one of the first. That's after whom the femto is named. And he was famous for doing quick calculations in his head. Yeah. And these are known as Fermi calculations. I'll just give you a little example. So again, these are order of magnitude calculations. Okay, you just do quick calculations, and of course you have to know some stuff. Okay. So let's calculate something that humanity does. What do you want to do? You want to calculate the amount of food eaten per year, per day by all of on Earth by all of humanity, or in their lifetime. What do you want to do? Let's calculate how much food humanity will eat in 100 years. Okay. So again, you have to know some stuff roughly. Okay. What is the population of the Earth? I'm sorry? Okay, so we'll make it 10 million. 10 billion. Okay. So that's the population. 100 years. How many days in a year? Yep. 365. 4 days per year. Okay. Remember, I gotta be able to multiply in my head. Okay. How much food do you eat per day? How many pounds? 4 pounds. Okay. A quarter pounder, let's say 4 times a day, 1 pound, 2 pounds. Okay. 2 pounds a day. 2.5 pounds a day. Okay, so there, and the reason I did that is 2 times 4 is that's 10, that's 1,000, 10 to the 5, 6, and 15. 10 to the 15 pounds. 10 to the 15 pounds of food are eaten by humanity in 100 years. That's a Fermi calculation. Again, is this answer exactly correct? No, it's a ballpark estimate. Okay, and that's the point. Again, so Mr. Fermi was famous for this. One famous story is when the first atom bomb was exploded. Mr. Fermi was present, and apparently he took a piece of paper, threw it in, tore it up into bits, and when the bomb exploded, he tossed this pieces of paper. And from how far they fell, he could calculate the yield of the bomb within 3% accuracy. You guys have seen golfers throw grass to assess the wind speed? Mr. Fermi did that for the yield of the bomb. All right, significant figures. Okay. So measurements can be accurate and not precise, or they can be precise but not accurate. Okay. So these measurements are precise, but they're not accurate. Okay, and these are precise but not accurate. Okay. So that's where you want to be here, and then make the errors smaller and smaller. Okay. The precision of a measurement is conveyed by the number of significant figures. Okay. So for instance, if I ask you to measure the width of this room, and let's say you say it's 25 meters, by doing this, what you've said is the precision is in the last digit. So you're telling me it's 25 meters plus or minus 1 meter. Okay, so that's the implied information. If you tell me that it's 5.6 meters, then it's plus or minus plus 1 meter. That's the implied. Okay, you measured it to an accuracy of 10 centimeters. If you tell me it's 25.65 meters, you measured it to an accuracy of a centimeter. Okay. You measured it to an accuracy of a millimeter. If you give me that number, I know you're lying. All right, so this thing has two significant figures, this thing 3, 4, and so on. Okay, so the number of significant figures tells you how accurate your measurement is. Okay. All right, that's significant figures. All right, we'll stop here.